Okay. So since everybody has a glass of wine, so we hear a lot of thanking. So in fact, there was a huge group of people which worked for success of both of these events, and it was actually very collective work. Yes, so unlike some other conferences, we had very nice and very collaborative team, which was formed by Maria Levares, who is here, Luis Renato Fontes from São Paulo, who just left, and then you didn't see, unfortunately, Servet Martinez from Chile, who couldn't come, and Roberto Fernandez, who is originally from Argentina, and now he is in Holland. So all this selection of people, discussions, it was not so simple to select because, of course, the world is full of very interesting work, very interesting scientists, and I would like to thank, first of all of them, and at the second level of preparation, organizing committee, which was formed by Bernardo and Leandro. It was really great pleasure to work with all of them. And actually, success of meeting lies on their shoulders. So let us thank and lift our glasses for them.
Hello.
Let's start our short talk section. The first speaker is Alessandra Bianchi from Università di Bologna. Go ahead.
Yes, thank you. So first of all, I would like to thank the organizer for giving me the organizers for giving me the opportunity to participate at the school and give a talk here. I'm very happy. I'm really enjoying this time. So the work that I'm going to present is the result of a collaboration I started already 3 years ago together with Anton Bouvier from the University of Bonn and Di Maioffe from the Technion of Haifa. The main object of the research, of our investigation, was a study and the characterization of metastability in the framework of stochastic dynamics. So in a few words, what is metastability? It's a very common phenomenon of nonlinear dynamics related to the first-order phase transition. Very generally speaking, it can be characterized by two properties. That is the existence of an apparent local equilibrium and the presence of two or at least two time scales. So that on a short time scale, the system will reach an apparent equilibrium, but indeed it will remain confined just on a portion of the space. As you see in the picture, say that for in a short time scale, we will see the system just remain in one portion. But then, if we wait enough on a longer metastable time scale, we will see the system move to another region, toward a new equilibrium. The aim of our investigation is indeed to characterize this time, this metastable time. The model we studied is the co-revised model with random field, which is indeed is an Ising model on a complete graph. In Cabezas is a model for a system of n particles, where to each particle is associated an Ising spin variable taking value plus or minus 1, so that the configuration sigma describe the system, and the energy of our configuration is given by this random Hamiltonian, where randomness is contained in this term, which is the interaction between spin and the external field. HI. Here we will assume that the external field HI are IID random variable with continuous distribution. We will also assume that the distribution has finite support, but that's the only assumption that we ask for. So as usual, at the equilibrium, the system is described by the probability Gibbs measure mu n of sigma that you see here, which of course depends also on the particular realization of the random field, while the evolution of the system is given by a global dynamics, which is a Markov chain sigma that I denoted by sigma n on the set of configuration, reversible with respect to the Gibbs measure mu n. This assures us that the dynamics converge to the equilibrium measure as we want. And there are many possible choices for the transition probability. Here I wrote down the transition probability corresponding to the metropolis dynamics, but I don't want to stay on that. So as a mean field model, it's quite natural to introduce the magnetization as the order parameter. The magnetization m of sigma is just the sum of all the spin normalized by n, taking value on this space gamma n. And you see here. So of course, due to the interaction with the random field, we cannot just write down the Hamiltonian as just a function of the magnetization, right? Still, using sharp large deviation technique, we proved that the induced measure on this on the set of magnetization, namely the Gibbs measure of a configuration which have a prescribed magnetization n, take the form like say of a Gibbs measure with a new energy function Fn of n. Fn of m, I didn't stress this in the notation, but is itself a random function depending on the realization of the field. But the important point is that asymptotically, the profile of F is almost surely, pH almost surely deterministic, say. In particular, the critical point of this function F are solution of this equation, okay, which is a deterministic equation. Now, depending on the choice of beta on the distribution of the field, we can have many different landscape. For example, something like that. Okay, this is a situation that we recognize as metastable. So in general, what we want to do is to measure the time the system needs to move from one local minimum, M1, to another local minimum. And now the dynamics is microscopic, right? Because it depends on the Hamiltonian. So we first have to project on the space of configuration omega. I call it omega. Okay. So say that A and B are the corresponding set the sets corresponding to the minima M1 and M2. The question is, if we start from a particular configuration, sigma in A, how long it will take the dynamics until reach the set B. So, more formally, as I said, let M1 be a local minimum of F, and here I denoted by capital N the set of deeper minima. In the previous figure was just one. And then I denote by A and B the corresponding microscopic set, okay? And now I denoted by tau B the heating time in the set B. So the first n such that the dynamics reach the set B, right? As usual notation. Now what we ask is what we can say about this metastable time. This is this denotes the average along all possible dynamics starting in a fixed configuration sigma in A. Okay? Now, a first result has been obtained using the so-called potential theoretic approach. Potential theoretic approach has been introduced in a series of papers by Bouvier, Eckhoff, Klein, and Gerard. from 2001 to 2004. This method provides a very useful formula for the metastable time in terms of capacity and the potential function. And if one is able to evaluate this quantity, then one can obtain a very precise result. What we prove is indeed that denoting by Z the minimax between the local minimum 1 and M. So let me go back to the figure. Z is just this saddle point here. Okay. Then we obtain that the metastable time average with respect to this probability measure that I will describe in a minute is given by a quantity that we know explicitly, so as a complicated formula, so I didn't write it here. But the leading term is this exponential term in beta n, and then here we have the difference between f in z, the saddle point, and m1. So again, coming back to the picture, what I'm saying, what is this difference is just the I of this valley. And the result is just with an error that goes to 0 when n goes to infinity. Now, coming back, what is this probability measure nu A? It's a probability measure on the set A, proportional, I mean, this is just a normalization constant, proportional to the Gibbs measure in sigma, and the probability starting from sigma to it B before A. So, say, this measure is somehow is what came from the method, okay? In the sense that if we want to control the quantity that involved in this formula, we need to average with respect to this measure. But now, a natural question is, does the result really depend on this measure nu A? Or equivalently, under which assumption can we deduce pointwise estimate from this mean field estimate? So what we believe in general is that the result should not really depend on the particular initial configuration. From a heuristical point of view, in fact, the system, before performing a transition to a set B, remained for a very long time around the region A, coming back very often to the A valley. Okay, and so in general, one believes that the system relaxes to the measure, to the Gibbs measure restricted to A in a short time. But once the system relaxes to the Gibbs measure restricted to A, it loses memory of its initial state, and then what we can do, if we can prove that this mixing time, this relaxation time, is much shorter than the metastable time, then we can deduce that indeed the particular configuration which we start doesn't affect the metastable time, first of all. Second, once the system has relaxed, then the return time to A are just an ideal random variable. In particular, the number of returns to A is a geometrical random variable. And this suggests that the metastable time has to be an exponential random variable. This is indeed what we proved, but before giving the result, I need to introduce just a bit more of notation that somehow give the idea, one of the idea at least, which is in both the article, both the result. So first of all, we fix a new parameter, L in N. Essentially, we are performing a cross-graining. So what we do is first we made a partition of the support of the variable H, or the distribution of H, in subset Ik, in L subset Ik. This partition induces a random partition of the set of particles in the sense that we group together all the particles or vertices that are associated with the value of the random field that belongs to a given set, subset IH. And then we introduce this order parameter. For every k from 1 to L, we just compute the magnetization inside these boxes lambda k, again normalized by hand, and then we denote by this bold M the vector, the L-dimensional vector, with entries, this quantity mk of sigma. So why we do that? A very brief idea. After define this variable, the Hamiltonian can be written as just a function that depends only on this L-dimensional parameter, this L-dimensional magnetization, plus a quantity which is small in L. So as bigger is L and better is this approximation to a function which just depends on a parameter living on a dimension independent on n, on capital N, so on a finite dimension. Now the main point is that, again, using sharp large deviation technique, we can prove that the induced measure on this set, L-dimensional set gamma L, again, can be expressed as like a Gibbs function with an energy function, as a Gibbs measure, sorry, with an energy function Fn of this bold M, which of course is a random quantity depending on the realization of the field. But now, the main observation is that the critical point of this function Fn, defined on the L-dimensional space, are in correspondence with the critical point of the function f of m defined on a one-dimensional space. In the sense that to every minima, it corresponds a minima, and to every maximum, it corresponds a saddle point with just a unique negative eigenvalue. In particular, if we consider this set A of L, which are just a set of configuration sigma with magnetization corresponding to a minima of F, this set will be a subset of A because of this correspondence. Right? And so finally, we have the result. What we prove using coupling techniques combined with some renewal arguments, we prove that, first of all, for L large enough and pH almost surely, indeed the metastable time do not depend on the initial configuration on this set AL. Okay, so for every two configurations, sigma and eta in AL, this time the metastable time is the same, plus an error which is small in N. And in particular, this time is equal to the average time we compute that I presented in the previous theorem. Moreover, again, pH almost surely, we have the distribution for every configuration sigma in AL, the distribution of the metastable time normalized by its average converges to an exponential random variable with mean 1. So the main idea was to use this coupling technique that was, at least from a technical point of view, suggested by this article from Levin, Lutzak, and Perez, where they study just the query-wise model. But the proof is much more involved than this somehow. Anyway, there is no time to neither to give a sketch of the proof, but if someone is interested, I can give you the detail. So thank you. Previous.
If you were not concerned with the precise value of the expectation, this
Yeah,
could be obtained in a different way also.
In the, do you mean in the Friedland-Wenzel, with the Friedland-Wenzel technique?
Yeah.
Right. But this result all for a finite temperature. I mean, that's made in that somehow the difference, the advantage of using this technique. But it's true that.
Our next speaker is Manuel Cabezas from PUC Chile, Santiago.
Yes, please.
Go ahead.
Well, first of all, I would like to thank the organizers. And I will talk about randomly traveled random walks and environments. This is work in progress, and it's joint work with Gerard Benarous and Roman Roifman. So we're first going to give up some examples. We will start by considering a regular tree, and then we perform percolation on that tree. So we can construct the incipient infinite cluster. We can construct it by conditioning a critical cluster to survive up to generation n, and then taking the limit. So we can see that this incipient infinite cluster has just one single path that goes to infinity, that is called the backbone, and from each vertex of the backbone, there emerges a random finite tree. So we can see that this sequence of random finite tree is an IID sequence of critical percolation clusters. So we can draw this incipient infinite cluster like this. It's like n, and from each side there emerges a critical percolation cluster. So now we can make a simple random walk on the incipient infinite cluster and project this simple random walk to the backbone. So each time the simple random walk is exploring the cluster that is attached to site Z, we will just see that our walk is fixed on site Z. So we will have a symmetric random walk on M, but we'll have random jump times. This result is due to Kesten. Now we can make another example, another similar example. We can perform now invasion percolation on our regular tree. So we can see again that the invasion percolation cluster has just one single path to infinity, which is called the backbone. And from each vertex of the backbone, there emerges a a finite tree. But this time, this finite tree is not a critical percolation cluster, it's a subcritical percolation cluster. And the parameter of the percolation depends on the site. And we know that as n goes to infinity, the parameter converges to the critical parameter. result is due to Angel, Goodman, then Hollander, and Slate. So we can, again, consider a simple random walk on this invasion percolation cluster, and we can project it to the backbone. So now we're asking about what are the possible scaling limits of these processes. A third example is a well-known example, is the Bouchaud trap model. This time we pick up a sequence of IID random variables. We say that the sequence of IID random variables has heavy tails. I forgot to say here that gamma belongs to 0, 1. So the sequence of random walks are heavy-tailed, and we construct a process by stating that each time that the process visits a site, it stays there an exponentially distributed time with mean tau subset. And X, then constructed in that way, is a Bouchaud trap model. The scaling limit for this process is the Fontes-Newman singular diffusion, which is a time change of a Brownian motion is a speed measure change of a Brownian motion by a random measure. So one of the key ideas on the proof of this theorem is that each rescaling of the Bouchaud trap model also can be seen as a speed measure change of a Brownian motion. So we can see that convergence of measure implies convergence of processes. This is a theorem by Stone. And then we can use that theorem to prove convergence of the Bouchaud trap model to the Fontes-Newman singular diffusion. And in more dimensions, this process converges to the fractional kinetic process. These results are out to Benarous, Cherny, and Mountford. So now, which are the results that we have? We have that the scaling limit for the walk on the IPC projected to the backbone is different from the scaling limit of the walk on the IIC projected to the backbone. And the scaling limits are neither Fontes-Newman nor fractional kinetics process, so there are new processes appearing. Neither Brownian motion. They are subdiffusive processes. And the scaling limit for X1 is a particular case of randomly trapped Brownian motion. So I will explain what randomly trapped Brownian motion is, but first I will give the definition of randomly trapped random walks. So we pick up a probability measure over the probability distribution on the positive reals, and then to each side we assign a probability measure in an IID way according to the probability measure P. So now we construct a symmetric random walk by stating that each visit of this random walk to a site lasts time distributed according to nu subset. And in this case, XP will be a randomly trapped random walk. This is the definition of a randomly trapped random walk. So the Bouchaud trap model is a particular case in which the times are exponential times. Also, the walk on the IIC is also a particular case of a randomly trapped random walk, in which the time I choose depends on the shape of the cluster that is attached to each site. And the walk on the IPC is almost a randomly trapped random walk. It's not a randomly trapped random walk because the times are not identically distributed, because the parameter depends on the site. But it's almost a randomly trapped random walk. So now, what is a randomly trapped Brownian motion? A randomly trapped Brownian motion is a time change of a Brownian motion. Now, how we construct this time change? So we first pick up a Poisson point process on R times R plus. So here we have a Poisson point process with intensity measure V to the -1 minus gamma. Again, gamma belongs to 0, 1. Now, F will be the set of Laplace exponent of subordinators, and a subordinator is an increasing Levy process. So we pick up a probability measure over the Laplace exponents of subordinators, and then we pick up an IAD sequence of Laplace exponents with distribution F. Once we have chosen this sequence, we pick up a sequence of independent Levy process with Laplace exponents F sub I. So the idea here is that each side, xi here, will represent a trap. A trap will be a side in which my process will spend a positive time. So to each side, I will assign the following process. To xy, I will assign the process j bar I, which is just a rescaling of the process ji. So the important thing is, to each side, I assign a process, a subordinator. So my new process will spend a positive portion of time at each trap, and the time will be this process jy, which is associated to this point. This point is a process associated with j bar y. And the time spent there will be the process evaluated at the local time of the Brownian motion. So when my Brownian motion is at time t, I now draw the local time of the Brownian motion at time t, and to each side xy, I assign the process j bar of I, and the time spent by the new process on this side will be jy, j bar y, evaluated at the L xy t. So then I sum over all the atoms and I get the time, the total time spent. Then I invert the function and I will get the randomly trapped Brownian motion. In the case that all the processes J bar are the identity process, a deterministic process, we will get a Fontes-Newman singular diffusion. Now we will have two assumptions to get convergence of randomly trapped random walks to randomly trapped Brownian motions. To each probability measure, we assign its expectation. So if mu is a probability measure, m of mu will be its expectation. So the first assumption is that this expectation has heavy tails as a probability distribution. So the first assumption is a heavy tail assumption. The second assumption is a bit more complex. So we pick up a regular conditional probability of P given M, and then we pick up P epsilon, a sequence of probability measures on the positive reals defined as follows. So P epsilon is like the probability P conditioned on have expectation epsilon. Now we define the Laplace transform of our probability measure. But now I have to say something. Suppose our work has given epsilon minus 2 steps. So it has a range of about epsilon minus 1. So the deepest trap found, it has an order of about epsilon minus 1 over gamma. So here I am considering the Laplace transform of a deep trap of when my work has given epsilon to the minus 2 steps. And now C of epsilon will be the Laplace exponent of a process which has given about epsilon minus 1 steps, and each step has a distribution of a visit of a deep trap. So when my work has given epsilon to the minus 2 step, it finds a deep trap of order epsilon to the minus 1 over gamma, but it visits that trap epsilon to the minus 1 times. So this will be like the Laplace transform of the time spent on a deep trap. So we want this function to converge in distribution. It's a random function because the probability distribution, P of minus 1 epsilon over gamma, is random. So now we say that F is the probability distribution, which is the limit of the distribution of C sub epsilon. Now we pick up a randomly trapped Brownian motion, we rescale it, and then we will have that this randomly trapped, it's randomly trapped random walk, we rescale it, and we have that this randomly trapped random walk will converge to a randomly trapped Brownian motion. For the case of the IAC, for the work on the IAC and the IPC, I want to say that this assumption holds, and for that, we have to see the time that a random walk spent on a critical cluster, critical percolation cluster, and I'm conditioning on the critical percolation cluster to be big. I'm conditioning to be a deep trap. So condition a cluster to be deep is the same thing to conditioning to have large numbers of vertices. So we know that a critical percolation cluster conditioned on having n vertices converges to a continuum random tree. And then we want to see what happens to a random walk on a critical cluster conditioned to have n vertices, and we know that a random walk conditioned on having n vertices converges to a Brownian motion on the continuum random tree. The first result is of Aldous and the second of Croydon. Now, the main idea of the proof of this theorem is to mimic the theorem or the strategy of the proof of the convergence of the Bouchaud trap model to the Fontes-Isupi-Newman singular diffusion. The problem here is that a randomly trapped random walk is not a speed measure change of a Brownian motion. So we have to define something more general than a measure, and to allow and to construct a Brownian motion on that thing. We will call it an environment. So we will define something which is an environment, which will be our generalization time. Well, the idea is to define a generalization of a measure, and instead of assigning to each set a number, we will assign it a subordinator, which is a process. Then, well, I have no time, but we can define Brownian motion on that environment, and then we can prove that convergence of environments will imply convergence of processes, which is like the theorem of Stone, a generalization of the theorem of Stone. And then, well, that's the main idea. That's all. Thanks.
Always of the same exponent.
No. No, the exponent is also random. So there's another level of randomness. There are two levels of randomness.
Or, thank you. Or, yeah, very sound. Thank you very much. So there will be no speaker after me, so I have to entertain you instead of him. First, I want to thank the organizers for this nice meeting with nice people at a nice place. Everything was excellent. I speak on behalf not only of me, but all the short speakers who spoke before me. Now to the matter. 4 years ago, the Porter and Mice published an article which they called Stavska's measure is weakly Gibbsian. In other words, they proved that a certain measure, known as Stavska measure, is not too bad. At least it is weakly Gibbsian. Generally, mathematical results should come in pairs. For example, if you have upper estimation of some quantity, while it is alone, you don't yet know how close you are to the quantity itself. So it is better to have also lower estimation of the same quantity. And then, if the difference between them is small, you can say that estimation is good. So, in fact, what I shall speak is the complementary result to this. They prove the Stavska's measure is not too bad. I shall prove the Stavska's measure is not too good. But first, it is not duty of every student to know what is Stavska's measure. I must tell you that it is the non-trivial invariant measure of the Stavska process. And now I must tell you what is Stavska process. So, we have a space 0, 1, Z. This is elements of this space are infinite in both directions, sequences of zeros and ones. And M large is the set of probabilistic measures on this space, more exactly on this sigma algebra generated by cylinders. And operator P transforms measure into measure, and measure is called invariant if P mu equals mu. Now, what is the Stavska measure, which is mentioned here, is the invariant measure of this operator, which I am going to define. The operator has two parts, deterministic and random. First, we apply deterministic, then random with parameter epsilon. Epsilon is the only parameter here. Deterministic, if we x is one B infinite sequence of zeros and ones, operator D acts on this measure because it is deterministic. And it is very simple with the index I is minim of xi plus 1. In other words, if every point which has is in a state 1 goes to 0 if its right neighbor is 0. And R epsilon means simply that every 0 goes into 1 with probability epsilon independently of all the others. You can see that operator D favors zeros and operator R favors ones. So we may expect something interesting to happen. And in fact it does. This operator P has a certain kind of phase transition. Namely, if epsilon is large enough, for example, greater than 1/2, or the only invariant measure of this operator is concentrated in the configuration all ones, namely P delta 1 equals delta 1. This is true for all epsilon, from 0 to 1. But for small epsilon, there is also another invariant measure, more interesting, and generally we, of course, want to describe invariant measures of random processes. So mu invariant equals mu invariant. this measure exists if epsilon is small enough, for example, less than 1/10. So there is some critical value of epsilon such that when epsilon is greater than this critical value, this is unique invariant measure of this operator, while when epsilon is small enough, the system has two different invariant measures. In fact, of course, more than two, because you can take any linear combination of them and also get an invariant measure. So as soon as there are two invariant measures, there are infinitely many of them, but two essentially different. Now, so this is the measure we are speaking about, and which they call Stavskaya measure. I shall not define what is weakly Gibson, because it takes time which I don't want to spend. I understand that all of us are tired and a little drunk. But instead, I shall define another thing which is more convenient for me now. I shall define what is a poly-Markov measure. Poly-Markov measure. First, I define what is Markov measure. Instead of two elements, 0 and 1, we can take any finite set, call it alphabet, call its elements letters, and define all the same. So A is alphabet to the power of Z is the sequence of B infinite sequence, is the set of B infinite sequences of letters, that's elements of A, and we call a measure mu is Markov if as soon as we fix the state of a certain point in this B infinite sequence, what is on the left side is independent of what is on the right side. And after that, since I have defined what are Markov measures, I can define what are poly-Markov measures. Imagine that the alphabet A consists of two parts, A0 and A1. The intersection of them is empty, and we can speak about certain map, let's call it M, which maps every letter of A into this set, namely A0 maps to 0, A1 maps to 1. And a measure on the configuration there is called poly-Markov if it can be obtained from some Markov measure under this map. And I can prove that Stavskaya measure is not poly-Markov. This is very close to what those guys did. I mean poly-Markov measures are similar to what they did. And now I shall tell you the main idea. Let us call Qn a mu invariant of 1, 1, n places. That is, Qn is probability that certain n places consecutive are filled with ones. I shall prove that the Stavskaya measure has the following property. There is a constant, positive constant C, such that Qn is greater or equal C times, let's write it this way, sum from I1 to n Qi times Qn minus I. First observation, a poly-Markov measure cannot have this property. Because for a poly-Markov measure, these quantities behave as a geometrical progression. While if they behave as a geometrical progression, then this cannot be true. Because every product of this sort is roughly this thing. But the number of them is n. So it is greater or equal to constant times n. Constant times n times qn. And this factor n makes it impossible for a polymarkov measure to have this property. But on the other hand, I am going to prove in a few minutes that Stavskaya measure has this property. Namely, why? If we have here k ones, and at another place we have L ones, and something between them, then on the next step of our operator, this 0 with a positive probability will be filled with 1, and we shall obtain k plus L plus 1 once. But in fact, the deterministic operator will decrease this length by 1, so we shall have k minus L. Or we can denote it I, this n minus I, and this n. And all they contribute to the probability that this is filled with ones. So probability that this is filled with ones is greater or equal than a constant times probability that here we have ones and here we have ones. But this is what is written here. And that's all. Any question? Please.
So, in your argument, your final argument, it seems you use a kind of independence?
Right. Yeah, I deceived you and you found it. No, of course I didn't use independence. But I used something which is similar to independence. That is, there is a special property of, well, almost independence. If the measure is polymarkov, then if you are here, then you are in that part of that matrix. You see, we can use here a theorem of Perron-Frobenius to notice that, in fact, here may be necessary to have, well, in fact, I'm telling you two different things at once. One, that for Stavskaya, we have inequalities that presence of ones here cannot decrease presence of ones here. So the fact that this is true and this is true is not less than the fact that this is true times the fact that this is true. And something similar even for much more general operators. This can be proved also, not this inequality, but it can be proved that probability of this combination is greater or equal than some positive constant times probability of this times probability of this. But this is more complicated. Okay? More questions? Uh-huh.